Hey Chemistry, Mrs. KJ here, going over part 3 of the Unit 3 lab. And I'm going to get this part started and then I'm going to go through and explain it because this takes a little bit of time for it to actually work. Alright, so if we notice both the beakers are at what temperature? 80 degrees. And I'm going to take them off the heat so they start to cool down. Alright. Zoom in a little bit so we can see a little clearer. Alright, so in beaker A, I have 32 grams of solute. In other words, I took one of my chemicals and I measured out 32 grams of it and I put it in here. I mixed it up and dissolved it, and it was at 80 degrees. In this beaker, I had 37 grams of solute, or of my chemical. I mixed it up in here and I had it at 80 degrees. As you can see, the solute is dissolved in both cases. Okay, so what we're going to do now is basically the opposite of what we did before. Before, I had the beakers at different temperatures and we added the chemical to see how much would dissolve at each temperature. And then we made a beautiful graph showing that. And now what we're going to do is we're working backwards. Now the chemical is already dissolved in here, and what I'm going to do is let it cool down and see when the chemical comes out of solution. So what that means is it's going to look like little snowflakes are appearing on the side of the beaker. And what those snowflakes really are the chemical. It's either the KCl or the KClO3, or maybe they are both KCl. Maybe they are both KClO3. We don't know. We call it an unknown in chemistry. And so we're working backwards to see, okay, what chemical did the chemist put in here? What chemical did the chemist put in here? We're going to record the temperature that we first started seeing the solute come out of the solution. So the water was too cold, it couldn't hold on to it anymore, and you're actually going to see the solute appear. So we're going to record that temperature and how much there was. Then we're going to plot that point for beaker A and do the same thing for beaker B. We're going to plot the point on here and see, are they closer to our blue line, which means the chemical was KCl, or is it closer to our red data, which means the chemical was KClO3. So beaker A started with 32 grams of some unknown chemical. It's one of these two, but we're not sure which one. Beaker B started with 37 grams of one of these two chemicals. We're not sure which one. We're going to record the temperature at which the solute first was observed in degrees Celsius. So again, we're going to wait and see until we can see the little crystals on here, and that tells us that at that temperature it's saturated with either 32 grams, or at the temperature when we first see it, this chemical was saturated with 37 grams at that specific temperature. And if you take a chemistry class in a brick and mortar school, you will find out that there actually is a lot of waiting in chemical labs. So while you're waiting, the best thing to do is answer some of the other questions. So let's go ahead and do that right now. All right, question number 1. Using your data, state the relationship between temperature and solubility. Hint, there must be data in your answer. I suggest comparing two specific points. All right, so we want to see what happens when the temperature increases. So let's look down here. When the temperature is how much? 5 degrees Celsius. We could dissolve about how much? There was about 5. I think my points keep bumping on me. Sorry about that. There was about 5 degrees. And when we go all the way up here to what temperature? 70. Now, how much do we have? We have about 33. All right, so when the temperature increases, what happens? The amount of solute that we need for it to be saturated also increases. So when temperature increases, the solubility increases. All right, and so that was our first question. When the temperature increases, solubility increases, or in other words, the molecules are moving faster. Therefore, they are having more collisions. Therefore, dissolving will be faster, and you can dissolve more. Okay, there's more craziness going on, so it can spread the chemical out even more. Now with this, we're cooling off to see at which temperature we can no longer dissolve this much of the chemical. So I want to check back in over here with our data, and we're right at around 66 degrees. And do you see any change yet? Nah, it still looks the same. It's gone down almost 15 degrees, but that's okay. We will keep letting it cool off. And we're going to continue to let it cool off some more. And what do you notice? What do you notice? Over here, right at around 65 degrees, you can see what looks like snowflakes. But it's not snowflake, it's the chemical coming out of solution. The water is too cold to keep it dissolved. The water is too cold to keep it all dissolved, so we're starting to see some chunks. And it's crystallizing on the side of the beaker. All right, and you can see there's a bunch on the bottom too. So that started at about 65 degrees, and that was beaker B with 37 grams. So let's add that to our data. We said at about 65 degrees. All right, and let's make this one orange. Let's make an orange dot. So let's put that on our graph. And do I need my dot to go to the left or to the right? I need it to go to the left, right there on 65. And I want it to go up to 37. All right, so we have 30, 32, 34, 36, 38, 37. Okay, so what would you say? Is it closer to the blue line or is it closer to the red data? I would say it's closer to the red data. Therefore, what does that tell you about the chemical in beaker B? The data point is closer to the red data, which tells us the solute used in beaker B was KClO3, which we know from looking at our legend up here. All right. Now, the other beaker, beaker A, we know it's going to be at a lower temperature because why? Because there's less of the solute. There's only 32 instead of 37. So we know that that one is going to be a little farther down, and we just have to wait and see what temperature it's going to be. So it's instead of at 37 grams, it's going to be down here at 32 grams. So we can go ahead and put that in right away over here at 32 grams. So we're ready. And let's make that one green. All right, we want it right at 32. And now we'll wait to see where we put it in the temperature range. And let's see how it's coming along for us. Ooh, look at this. What do you notice? As it's getting colder, there is a lot more of the solute that you can see. And hopefully that makes sense because now the molecules are going slower, and the slower the molecules go, the less and less of the solute that can be dissolved. So more of it has to come out of solution. It is definitely saturated, and it's becoming more and more saturated as we let it cool off. All right, so I'm going to hit the pause button for a little while because it takes a while for it to continue to cool, and we'll check back in. Actually, while we're waiting, we'll go ahead and answer some more questions. Question number 2. Using your data, compare the solubility for each substance tested. Hint, there must be data in your answer. I suggest comparing a point from each line on the graph that has the same temperature. So in other words, I want to know at the same temperature. So let's take 30 degrees. At 30 degrees, which chemical is going to have a higher rate of solubility? Or which chemical is going to be able to dissolve more at the same temperature? Well, at 30 degrees, the blue one, our KCl, can dissolve about 38 grams, and our red one can dissolve about 15 grams. So we can say at the same temperature, KCl will dissolve more than KClO3. And we can see it all the way along. All these points are higher, so KCl at the same temperatures can always dissolve more. All right, let's go ahead and look at the next question. Use your understanding of atoms and molecules and of the kinetic theory to explain the results of the experiment in terms of collision theory. Okay, collision theory means atoms are constantly moving. And because they are constantly moving, they can dissolve things. Dissolving happens when molecules of the solvent hit molecules of the solute, and basically it breaks it down into little pieces. The warmer it is, the faster the molecules are moving. The more collisions, the more of the chemical is going to dissolve, and of course also the quicker it's going to dissolve. All right, looks like we have time for one more question. And this question is talking about how solubility is used in real life. So solubility, the phenomenon of dissolution of solute in solvent to give a homogeneous system, in other words, the fact that we're dissolving stuff, is one of the most important parameters to achieve desired concentration of drug in systemic circulation for desired anticipated pharmacological response. In other words, if you are sick and you need medication, you need to get the right amount of medication. If I have pneumonia and my 2-year-old daughter has pneumonia, we're both going to get the same medicine, but we're going to get different amounts. Why? Because I'm a lot bigger than my 2-year-old. And so I have to make sure I get the right concentration, the right amount for my body. Low aqueous solubility is a major problem encountered with formulation development of new chemical entities as well as for the generic development. So what that means is the fact low aqueous solubility. That means a lot of the medicine that we use, those chemicals, do not dissolve very well in water, but we need them to so our bodies can use them. Otherwise your bodies would just poop them out. Okay? Well, that's what happens to stuff you can't digest and use. So the drug companies don't want you to poop out the drugs. They want the chemicals, the drugs, the medicine to be used by your body to help fight the infection. This is also important if they're going to make generic, which cost a lot less. So they need to know how to do this. More than 40%, almost half, of new chemical entities, or in other words, more than 40% of all the new prescription drugs that they come up with, developed in pharmaceutical industries, are practically insoluble in water. That means it's like putting oil with water. That means they can't dissolve and your body can't use them. Solubility is a major challenge for formulation scientists. Any drug to be absorbed must be present in the form of solution at the site of absorption. So why do we need chemicals to be soluble? We need them to dissolve so that they can be dissolved inside your body, so that your cells can dissolve them, and then, once they're dissolved, your cells can use them. What could scientists do to combat this problem? What could they do to help increase how much the chemical is dissolved? Well, maybe they could say, okay, when you take this, you have to take it with not burning hot, but really warm water, because that would raise the temperature. That would help a little bit to start dissolve it, but then your body's always the same temperature, right? Okay, they can combine it with different chemicals. They can change little bits on the chemical so that it attaches in different parts in your cell. They can put it with other chemicals so that your body can absorb it. So there's a lot of different ways that they do besides what we talked about in chemistry, but it's a real life example, so I wanted to go over it with you. All right, let's look at this. We definitely have some of it coming out of solution. And look over here, it's almost filling up, right? It's getting so cold that hardly any can be dissolved in this beaker anymore. But at this beaker, at 32 grams of solute, it started coming out of solution at about 39 degrees. All right, so let's add this down here. It was at 39 degrees. And we want to move our dot over to 39. And which chemical would you say is in beaker A and why? I would definitely go with KCl because it's closer to the line. All right, make sure you email me so that I can put in your grades. If you have questions, let me know. Bye.